Okay, so now we're going to wrap up section one. We've got some important details here to look at. And so what's happening here is that up to this point, we've been using the yields on a bond to calculate its price, but it turns out that often it's more useful to be able to take the price of a bond and use that to calculate the bond's yield because prices are directly observable in the marketplace, whereas the yields are actually implied by the terms and conditions of the bond. And so if you remember the price yield curve that we defined once before, we have price in the vertical axis, yield on the horizontal axis. The curve looks something like this. It has a downward slope, of course, because the price and the yield go in opposite directions, but it's also not a linear function. It is a convex function. And that basically means that in this case, at least, the first derivative is negative. The second derivative is positive because the slope is becoming less negative as we increase the yield. Also, there is a geometric way of doing this. We can prove that a curve is convex if we do the following. If we draw a secant line to the curve, and everywhere that secant line is above the curve, that's another way of proving that this function is convex. Okay, so by constructing a secant line through the price yield curve, we can see that the secant line is everywhere above the price yield curve, which indicates that the curve is convex. Okay, now that actually proves to be advantageous for the investors, as we're going to see in the next section, because there's an asymmetry between gains and losses. So if, for example, let's just say that this is our price yield curve, and initially with a yield of 5% and a price of 1,000, the yield goes up to 6%. Let's say the price drops to 950. And when the yield drops to 4%, the price goes up to, let's say, 1070. The important detail here is that in one case, we moved up by 1%. In the second case, we moved down by 1%, but the impact on the price is different. Okay, so in other words, you can see that when the yield rises by 1%, the price of the bond falls by $50. When the yield falls by 1%, the price of the bond rises by $70. So that asymmetry between the two is because of the convexity of the curve. Okay, so the convexity of this function is responsible for the difference between the two cases. In other words, if the relationship was linear, then we would gain or lose the same amount. Okay, but instead, as you can see, investors are happy because a drop of 1% in yields adds $70 to our bond price, whereas an increase in yields by the same amount only reduces the price by $50. Okay, so convexity is a very valuable property of a bond. And again, we'll see in the next section that convexity is a measure that we can define to help us understand how curved this function is for different bonds in the economy. One more thing I want to mention before we go any further is that percentages can be somewhat ambiguous. So there's another measure of changes in interest rates that we often run into in the financial markets, and that is this notion of basis points. or sometimes abbreviated BP or BPS. And so the way it works is this: 1%, which is 0.01, is defined as 100 basis points. 0.1%, 0.001, is 10 basis points, and 0.01% is 0.0001, which is 1 basis point. So why do we need a measure like this? Well, like here's an example. Let's say, suppose that yield of a bond is currently, like we saw here, it's currently 5%. If we say that the yield has increased by 1%, this could potentially mean one of two different things. The yield increased from 5 to 6, meaning by 1%, or the yield increased from 5% to 5% of 5, I'm sorry, 1% of 5% to 5.05%. Okay, so in other words, because this is English, it can be very ambiguous. If we say the yield increased by 1%, then it could, in principle, mean either that it went from 5 to 6 or from 5 to 5.05. So you can see we have to be careful about that. So with the basis point system here, it's very straightforward, because this, in the first case, we would say that the yield has increased by 100 basis points. And in the second case, we say that the yield has increased by 5 basis points. And so it's pretty clear what we mean in this case. In other words, you often hear the term basis points. And in fact, one of the measures of risk that we'll see in section 2 is actually based on the notion of basis points. So we want to be aware of this. All right. Anyway, now, with all that being said, here's what we're building up to. You can see that the price yield curve is monotonic. Specifically, it's monotonically decreasing. So you can think of this as P of X or P of Y, actually. The price of the bond as a function of its yield is monotonically decreasing. And that means that Y1 less than Y2 implies that PY1 is less than PY2 for all Y. No exceptions. Okay. So why does this matter? Because this implies or guarantees and it doesn't have to be monotonic down, monotonically decreasing. Either way, as long as it's monotonic, the function is guaranteed to have an inverse. Why does that matter? Because in the case like this, as you can see, the price of the bond depends on the yield. But you could also make the case that the yield depends on the price. I guess you could write it as Y of P. Actually, you'd probably be better off writing it like this. Okay, so the yield of a bond is not directly observable in the market. It is implied by bond's price, maturity, coupon payments, etc. In other words, all the features of a bond combine to tell us the yield of that bond, but it is implied by the other variables. The market price of the bond is directly observable in the marketplace and is a result of supply and demand. So therefore, it is usually more useful, is often, let's say, useful to be able to compute um, the yield of a bond from its price. Okay. Now, unfortunately, unlike the price, taking the price from yield is easy. It's just a question of calculating present values. Okay. The price of a bond can be easily calculated as the present value of the bond's future cash flows, where the discount rate, the rate at which we're discounting the cash flows, is the bond's yield to maturity. All right. So remember the way we did this in the slides. Let's go back a bit. Here it is. Oh, actually, I realize now that these are R's. All right. Every half the books in the market use R, half of them use Y. I'll tell you what, just to avoid confusion, let's go back and change all these Y's to R's, just so that it's crystal clear that we're talking about the same thing. Okay. Very good. Okay. So now we got that straight. Okay. So here's the price. So it's easy to calculate the price. And remember too, the R is the yield to maturity. And so finally, the yield to maturity is defined as the unique rate of interest at which the present value of a bond's cash flows equals the bond's market price. Okay. So in other words, if we tried anything else, if R is too high, that means the bond's price will be too low, and vice versa. Okay. Now, so here's the issue we're up against. In order to determine the bond's yield, it is not usually possible to invert this function and solve directly for R. That would be wonderful, but it doesn't work that way. So instead, we have to resort to numerical methods. Specifically, root finding techniques, they're called. Okay, so remember, now numerical methods are simply a way of finding the value of a function without actually having knowing the function itself. So in other words, we have to use approximations sometimes. And so there's a whole branch of mathematics called numerical methods, and that's all that they do. It's kind of an interesting area of study, but every situation is a little bit different. So here, it turns out there are several of these available to us, and we're going to consider all three of these and just understand what they're doing. And they're referred to as the method of bisection, the Newton-Raphson method, and the secant method. These are all available to us to solve for a case like this, where we're trying to invert a function without actually inverting it. In other words, to use numerical methods to find the inverse of this function, or in our example, to solve for r. So the method of bisection is the most straightforward one. And so what it essentially amounts to is this. Um, the way I remember the first time I ran across this in one of my books, the way they described it was like trying to find a lion in a desert. I mean, it's a strange analogy, but what they're basically saying is that imagine here's your desert and here's your lion. All right, well, it looks like a rat, but let's say that's your lion. So what you do is you cut the desert in half and you say, well, he's not here. So let's cut this remaining half in half. Well, he's not here. Let's cut this in half. And let's cut this in half. And eventually you have to find the lion. If you keep cutting the area in half, eventually you have to find the lion. And so it's a brute force approach, meaning that you're going to use a lot of steps, but you will eventually find what you're looking for. It's not as efficient maybe as some of the other methods, but it does definitely work. Some of the others, there's no guarantee that they will find the solution. This one is, you will definitely find the solution. Okay, so, and of course, you notice the name that bisection refers to the fact that you're taking whatever area you're looking at and cutting it in half every time. So, here's what we have to visualize. Now, by the way, I do want to mention here that when you're doing this with yields to maturity, what we have to do is make sure that the yield curve itself has some regions that are positive and some that are negative. Otherwise, this technique won't work. Okay. So in other words, if you notice, what you've effectively done is taken the actual price yield curve and shifted it down by the price of the bond. Or in other words, think of it as subtracting that constant from every point along this curve so that you end up with this. And right here is what we're looking for. Okay, what you're seeing right there instead of a zero here, we have the market price, and this is the bonds yield to maturity. So in other words, in order to use the technique we're about to use, you can't just apply it directly to the original price yield curve. We have to have an area where it's positive, where it's negative. So this is how it's done. All right, so now how do we find this point? Well, we're going to choose 2 points on either side. So by the way, we're going to use slightly different notation here. We're going to call this f of x. And so you can see what's happening here is that here's where it crosses. We need to find 2 points that are on the outside of this intersection with the horizontal axis, meaning that A has to be less than this point and B has to be greater than this point. Otherwise, we can't find what we're looking for. So in other words, you would never put B over here or A over here. One has to be where the curve is positive and the other has to be where the curve is negative. Now, once we determine that that's indeed the case, what matters is now the signs of f of A and f of B. So in other words, if f of A times f of B is negative, that means that A and B are on either side of the root, it's called, right here. That's the root. That's what we're looking for. And or sometimes we say that A and B bracket the root. All right. Without that, none of this will work. All right. So we have to make sure that part is in place first. Now, what comes next? We're going to establish a midpoint between A and B. All right. So let me copy this in here so we can see it better. So once we've established that these A and B bracket the root, we need a midpoint. Here's the root. Let's say this is C. C is the halfway point between A and B. So when I put the C there, one of two things can happen. Either A and C are on the two opposite sides of the root, or B and C are on either side of the root. We have to figure out which is which before we can proceed any further. So you can see here that f of A is positive, f of C is negative. Which means that f of A times f of C is negative. And that means that A and C bracket the root. But as far as B is concerned, we don't care about B anymore. In other words, what we're going to do now is once we've established that this is the case, we're going to redefine B as this point. Okay, so see, this is how we're cutting the area in half. Like it's kind of like with the lion in the desert, but it's a little bit different because suddenly that C that we just defined is now the right endpoint of the interval that we're studying. And now we need another midpoint. Okay, let's say that that's here. So now with the new f of C has the same sign. Sorry, the opposite. Sorry, it has the opposite sign of f of B. Okay, so the new f of C, positive, f of B is negative. Their product is negative. So now all of a sudden, this C becomes the new A. And then we need another midpoint and another and another and another. And so you can see what's going to happen. We're going to keep alternating back and forth between the two. We're going to try different midpoints, test the signs, and see whether we now have a new left endpoint or a new right endpoint. Eventually, we're going to find the lion. In other words, the brackets will get awfully close. And now, of course, it'll never perfectly line up here. I mean, there will always be some inaccuracy. So before the process starts, we must establish a level of tolerance, it's called, which simply means how close do we need to be to the true root, or yield in this case, to be acceptable. Because otherwise this will go on forever, literally forever. Okay, so if you decided that you need to know the yield within 0.0001, well, that's fine. It'll stop when you've gotten closer than that. Okay, so you can establish now, of course, lower the tolerance that is needed, the longer this process will take. But it still won't take all that long. I mean, we're using modern computers that can execute a large number of commands in a very short period of time. So, when these methods were first invented, there weren't any computers. It was all done by hand. So efficiency was critically, critically important. And it still is, but it's not nearly as important as it was, let's say, in the 1950s. So even if this method of bisection isn't the most efficient method in the world, the fact that it's guaranteed to converge to the correct solution is a very powerful recommendation for it, because it's not going to be that much more time consuming than the other two, where there can be problems finding the right solution. In fact, they can get into a loop where they never do find the solution. So this is a very popular method, even though it might seem inefficient compared to the other two, because they have a different way of reestablishing the upper and lower limits. And for them, if the function is well behaved, we can often find the root that we need in just a handful of calculations. Okay, this might take a while, but again, at least we know that we're guaranteed to find the right answer. So that's the logic behind this method. Now, Newton-Raphson, by the way, yes, that is Newton, our old friend Newton from who invented calculus and half of physics, I guess. Newton-Raphson is very powerful, but it does require us to calculate the first derivative of our function many, many times. Now, that could be a real problem here because one of the unfortunate things about the price yield curve is that um, the price yield curve um, is not an observable function because there are only a handful of bonds available uh, to construct the price yield curve. In other words, that price yield curve covers every possible yield from zero up to whatever. We don't have enough information in the market to construct the entire curve. What has to happen here, there's a special technique going on behind the scenes. The curve is completed with one of several techniques. One of the more popular ones, which we're not going to have time to get into here, but it's something called cubic splines. So in other words, if you have to visualize, imagine that this price yield curve treasury market looks like this. Now, here's the problem. Even the treasury market only has a handful of maturities to choose from. So what's going to happen is if we try to construct this curve, you might have, let's say, well, all right, well, you're going to end up with gaps. This is what I'm building up to. It's not a continuous function. This function is not observable. And what has to happen is everywhere there's a gap, we have to find a way to fill it in. So the cubic splines are basically a special type of polynomials that are well suited for this type of application. In fact, you could think of them as being somewhat like a Taylor series, where you're sort of approximating a function with a polynomial of some kind. Okay. So that's kind of more like what you're actually getting. And so in other words, why did I even bring this up? This means that finding the first derivative of this function is not realistic. I mean, you can do some approximations, but you're not likely to be able to find the actual first derivative because we don't actually know the full function. And even if we did, it's assumed to be smooth and continuous, but that may not actually be the case in practice. So what that means then is that Newton's method is going to be a problem for something like this. But if you do use it, this is what it looks like. So in other words, for each x, xk we're going to call it, to get to the next x, to get closer to the root, we're going to take the current xk, as it's called, and subtract the ratio of the function evaluated at that point over the first derivative evaluated at that point. So now this is hard to draw, but let me see what I can do. Imagine we start, and this one requires a starting point of some kind. Let's say we start here. The next point might be here. And then we might have this point. And then we might, eventually we'll get to what we're looking for, but it's possible that we'll just need a handful of slopes to get to the root that we're looking for. But it's also possible that if the function is not particularly well behaved, you can get into a case where the slopes are just, um, say you're trying to do a sine wave or something ridiculous like that. You might find that the lines that you're generating, the tangent lines that is, are just alternating back and forth, and they will never converge to the correct value. So that is the kind of problem you could potentially run into with Newton-Raphson. For other types of functions, it works great, but for this situation, it's maybe not the best choice. Anyway, and then we also have the secant method, which doesn't need a derivative, but it does require a lot of information. You can see that this one could really take a lot of computational power, although if you're lucky, it might converge quicker than the method of bisection. And of course, remember the difference between a tangent and a secant. The secant cuts to the curve twice. The tangent just touches it at one point. Okay, so that's why we need so much information to come up with the secant method, because you need both of those points where the line is cutting through the function. And so this one can be very time consuming. And again, you run into that problem where the way it's designed, it may not necessarily converge to the right answer. So, if you really need to calculate a bond's yield to maturity, you might be better off using the method of bisection in spite of the fact that it could be somewhat slow. Okay, so now there's other methods too, of course, but the idea here is that once again, the yield of a bond is implied by the bond's price and other terms and conditions, or other features, let's call it. Whereas the market price of the bond is directly observable in the marketplace. All right, now, with all that being said, we can move on to section 2, where we're going to introduce some measures of interest rate risk. So now, why is this so important? Given that bonds are priced as the present value of the bond's future cash flows, and we have a copy of that formula right here. Or I thought we did. Here it is. So if you look at this algebraically, you can see very clearly that if you differentiated this function with respect to R, it's going to be zero. Sorry, not zero, negative. It's going to be less than zero, okay? So in fact, this is why the slope of the price yield curve is negative. So it's guaranteed to be negative. And so therefore, yields and prices move in opposite directions. Okay, so that being the case, even bonds with no credit risk, like treasury securities, expose investors to what we call interest rate risk. And all that means is that if you own a bond investors can lose money if interest rates rise. Okay. Now, what's interesting here is that each bond's sensitivity to interest rate changes is different. For example, if market rates rise by 1% or 100 basis points, one bond may lose 0.5% of its value, and another bond might lose, say, 4% of its value. Okay, so each bond has a different sensitivity to changes in interest rates. And so therefore, it's important to have a measure that we can use to compare them with each other directly. So it is important to have a measure that can be applied to any bond, which makes it possible to compare their sensitivities to interest rate changes directly. So you take a bunch of bonds and rank them from the least sensitive to the most sensitive. Okay, that's an important detail. So what measures can we use to measure the bond sensitivity? Well, there are quite a few to choose from, but we're going to start with a couple of very important cases for historical reasons. And they're known as duration and convexity. There's that word convexity again. Convex comes from the curvature of the price yield curve. Okay, so two of the most widely used measures of interest rate risk are known as, and then we have duration, as you saw, and convexity. Now, there's a long, oh, what happened here? Uh-oh. All right, let me move this stuff that I just created. Yeah, somehow it got put in the wrong spot. Let me just make sure everything's set up correctly. I don't want you to have confusing notes, that's for sure. All right, it looks good now. All right, I think we're golden. All right, I don't know how that happened, but there we are. All right, now there are multiple types of duration measures. It's not, there's not just a single one. The first type is known as a calling duration after the inventor or the developer, I guess might make more sense, the developer, whose name was Frederick Pauli. A more modern version of this is known as modified duration. It has um, more useful properties for analyzing interest rate risk than Macaulay duration, which, which by the way, Macaulay was an actuary. And what was he interested in studying? And I don't remember. He worked, it may have been an insurance company they worked for, who wanted to ensure that a financial institution um, always had enough funds on hand to cover its potential liabilities. Um, as an example, an insurance company collects premiums and then pays out claims as needed. So how do they make sure they have enough money? Well, the premiums are invested typically in something very safe, such as treasury bonds. And hopefully, the returns to these investments will ensure that no matter how many claims take place, the insurance company will have enough money to cover them. So, in other words, what you're trying to do is say, in this example, the invested premiums or the treasury securities that were invested in are assets, and the potential claims against the company are liabilities, meaning that we potentially could have to pay out money. So the goal is to ensure that the interest rate sensitivity of the assets and liabilities is as close as possible. All right. So if instead, um, let's say the sensitivity of the assets is greater than the liabilities, an increase in interest rates will reduce the present value of the assets rate more than the present value of the liabilities. Those they'll both go down, but the value of what you have to pay for your claims with has fallen more than the claims themselves. So you can see we don't want this. This is not what we want to. Insurance companies are conservative because they don't want to run out of money, and of course they're heavily regulated too. So Macaulay's idea was to make sure that we have a way of determining if there's an imbalance in the sensitivities of our assets and liabilities, because if there is, we have to do something about it. Because before he came along, there was really no way of saying, listen, these assets are more likely to be affected by interest rates than these liabilities. There is no way of directly measuring them. So his measure turned out to be hugely important. And of course, this is why it was named after him. But as far as investments go, this measure, call duration, is more difficult is difficult to interpret. Let's put it that way. It's not really the best choice for analyzing an investor's bond holdings. For this, a better measure, and one that's closely related, by the way, is known as modified duration. I don't think anyone knows who invented it because otherwise their name would be attached to it. But modified duration has the advantage that it can be interpreted as a derivative. In other words, well, we'll see when we get to the definition. A calculus derivative, I mean, not a financial derivative, a calculus derivative. And so that makes it much easier to measure the risks of these different bonds in our portfolio, compare them directly with each other. We're not interested in the assets and liabilities of a corporation. We're looking at individual bonds and how much their value might fall if interest rates go up. But luckily for us, the modified duration is so straightforward. It's almost amazing how it's just this close to the Macaulay duration. Once you know the Macaulay duration, it's not hard to convert it into modified duration. The convexity is a second order condition in the same way that the second derivative is the derivative of the first derivative. The convexity is a second order condition and can be thought of as the sensitivity of duration to changes in interest rates. In other words, the duration itself is affected by changes in interest rates. It's not a constant. So it's often important to be able to incorporate both duration and convexity in our measures. So, and a lot of this is going to sound very abstract until we actually do some examples. So, and when we do start using examples, we're going to have to do these in Excel because otherwise it'll take forever. But yeah, you can see the Macaulay duration. It's kind of an interesting idea. It involves the time. It incorporates not just the present values of these cash flows, but the time at which they're received. And we're going to go through a lot of numerical examples here. And then we're going to try to make some sense out of them. And we're going to see how they relate to modified duration and how it can be calculated. So you can see we got a lot of work to do here. So, oh, and here's how, again, how we show that a function is convex. This is the geometric argument. And we'll take a look at that. But anyway, so we'll be getting back to this next time we meet. So hopefully you've enjoyed this introduction to interest rate risk. But yes, we do have a long ways to go here. So we'll pick that up next time.